Hello and welcome to the lecture Decoder Only Transformer Model. In this lecture, we basically discuss on generative pre-trained transformer, popularly known as GPT. We start with understanding that decoder only transformer. Then we discuss one by one GPT architecture, pre-training and fine-tuning of the GPT. Then we discuss concept of masked self-attention and GPT with zero-shot learning, and then the application of GPT. Then we introduce another encoder based transformer model for vision application. In the last class, we have observed that BART is a very efficient model for learning contextualized embeddings. For what? And using transfer learning for other tasks. For example, classification. Now, although it is very efficient for learning these contextualized embeddings, it in general can't generate new sentence because it has no decoder part. It is an encoder only model. Now, if consider a situation that we want to generate a new output sequence, then BART may not be a very good choice. The answer lies in the form of GPT. The GPT uses only transformer decoder. So it's a decoder only model. No encoder is involved to generate new sequences from scratch or from a starting sequence. So let's try to understand what is GPT all about. Now, GPT, the full form of Generative Pre-trained Transformer, is a family of language models developed by OpenAI that generate human-like text by predicting the next word in a sequence. So it essentially predicts the next word. So it basically a decoder only model. So it has an inherent capability of generating text, sentence, or word. Unlike BART, GPT uses the unidirectional model that it can left to right, and it uses the transformer decoder as we said. This unidirectional property make it specially effective for text generation tasks such as writing, conversation, code completion, etc. Because all these tasks are basically in left to right. So as in other language model, it first pre-trained on large text dataset and then optionally fine-tuned for specific application. And this pairing, this pre-training and fine-tuning, enables strong performance across a wide range of natural language tasks. So this is all about this in a very naive or very simplistic way, the GPTs. Now here we can see the very brief architectural description of this GPT model. As we have said, this is a decoder only model. So that means it is a series of transformer decoder. This number is very hypothetical. It may be more, it may be less. So a series of decoder, it is given here as a part of this decoder only model. And every decoder is basically this transformer decoder of the actual model, but is proposed in this paper. Attention is all you need. So here we can see there is a masked multi-head attention. So it's a kind of self-attention. Will come what is masked. Then there is some add normalization, multi-attention, then feed forward and so on. So main these two things, masked self-attention that we have to understand and feed forward neural network. Now how this architecture work? That it is taken a part of the sentence. For example, for every action there is it is expected that this transformer model or transformer decoder model will generate the word equal. That is the target for this. Okay, so this is the way it is being trained. Now in this architecture, this transformer architecture and transformer objective used in this part left. So this is the basic transformer. So 12 times this character. It's a masked multi self-attention, multi-head self-attention, and layer normalization, feed forward, there is a receivable connection also, again layer normalization, and text prediction or classification. So input transformation for fine-tuning on different tasks. Now here you can see after this is the main architecture which has been pre-trained on large text corpora, and then it is fine-tuned with different tasks like classification. You can say this is the start token, then the text, then we extract, that means what information we are trying to extract, put this transformer and give a linear there. Entailment, that means that we have to try to find out some extract from this. So the premises, then hypothesis, so how it is logically linked in transformer model to the layers. Now here how to is similar, text 1 to text 2 and text 2 to text 1. So this we generally check, and multiple choice in. So these are the different application where it has been fine-tuned separately. So all structure inputs are converted into token sequence to be processed by the pre-trained model, followed by a linear softness there. So this is the, and after that it is been fine-tuned for a specific task. Okay, so this is the as a whole GPTs. Now it is two major things. One is pre-training, one is fine-tuning. As we have seen here, this is pre-training part, PGFS pre-training. Then after pre-training, we fine-tune for the each of the specific task. Some other task also. Now this pre-training process is unsupervised in nature. So what it actually do? It refers to the initial learning phase where GPT models are trained on a large amount of unlabeled data to learn the general language patterns without any task-specific supervision. So that we have to understand that basically it is kind of way it is being pre-trained. There is some tokens. What would be the next token? And that we know the next token because it is just text corpus. So in that way. So GPT learns by predicting the next token. That means word or subword, whatever. In a sequence using a raw text data and no human annotated labels are required. Let input sentence like the sun rises in the east. So this part is given to this GPT, and it is expected that it will. If it is not output this, there is a loss occur, then we calculate the loss and accordingly change the parameters or update the parameter so that it generates the right answer. This is how it is being trained, but it trained on a very large amount of text. So we can say the objective function of the GPT is the next token prediction, that is language modeling. So this model essentially maximizes the probability of the correct next word given the previous context. So this is the previous context, and we try to maximize the likelihood of the next token or next predicted token to be predicted. So that is the basic objective function. So if we do the step-by-step training process, first text is tokenized into sequences. Then GPT reads the token left to right. So if this is the tokens, it is tokenized. Then GPT scans left to right. Use the masked self-attention, so it only see the past tokens. No future tokens in this. Learns statistical patterns of language, grammar, fact, reasoning, etc. This reasoning cues, etc. So this is as a whole the pre-training process of the GPT. The next phase of training is the supervised fine-tuning. So it is the stage where the pre-trained GPT, that means this GPT model which already been pre-trained on a large text corpus. Then this model is further trained on a labeled dataset. Now this labeled dataset is not that much high. It's a small dataset to perform the specific task or more accurately. For example, this kind of translate hello to French, and this hello means bonjour in French. So this is a kind of annotated dataset or labeled dataset. So what are the specialized tasks or special tasks in this way this GPT can perform? This is question answering, then translation, that means the machine translation, one sentence in a particular language to another language, text summarization, chat based assistance, kind of chatbot conversations, code generation, etc. Now main thing that there is a two major thing in this GPT training. One is pre-training, where the general language knowledge been given or been learned by this model. This is unsupervised in nature, and this is a task specific fine-tuning. This increase or improve the task specific accuracy, but that is the supervised in nature. So these two are major aspect of the training of these GPT models. Now we have to what is the evolution of GPT models. In 2018 it is first been introduced. Then it is coming GPT-2 in 2019. It is known as strong text generation. Then GPT-3 in 2020, GPT-4 and beyond. This informed reasoning, improved reasoning and multimodal abilities. So in this lecture we discuss GPT-2 mainly, but it is the architectural training from the training purpose more or less same, but this has some improvement is there, so that we can understand the actual understanding and what are the basic know-how of the GPT models. Now GPT-2 is the second generation generative pre-trained transformer that is developed by OpenAI in 2019, as I've said, known for its strong ability to generate coherent and contextually relevant text. So this is the basic way, that is the basic motivation of behind the innovation of GPT-2. So it's a large-scale transformer-based language model trained on predict the next word in a sequence, enabling it to produce a paragraph of realistic text from the short prompt. So it's a prompt based textual knowledge or language based language model that can produce a kind of paragraphs or realistic text. So the model size is 1.5 billion parameters. This architecture is transformer decoder. This is unidirectional architecture. Training data is large text data set, web text, and the main objective is next prediction. By doing so, it understands a lot of things: language construct, how to submit information, some contextualize context and semantics of the text, and so on and so forth. So, what is the GPT-2 architecture? It is a very similar architecture. That is it, as we said in GPT architecture as a normal GPT architecture, that is the only transformer decoders. There is no encoder involved to generate a new sequence from the scratch or from a starting sequence. So this is basically. So it is these two. This is a masked input. Masked input means these tokens are not seen by the decoder at the time of training. So given these two input to the decoder, these two tokens, that is prior of this third token in this sequence or in this sentence, and it is expected that it generate this the proper output. Three main things: one is mask self-attention, one is about encoder decoder self-attention, and is feed forward neural network. This is the main decoder block. Okay, this is the as a whole a very simplistic diagrams or simplistic architecture of the GPT-2 model. Now first to understand how GPT works. For example, this GPT is a decoder only that we have to understand. It outputs one token at a time. So it is called autoregressive model. Why it is called autoregressive? The output token is appended to the input token sequence to be input for the next iteration. Now you see this. Now this prompt is being given. State Newton's third law of motion. Okay. Now first what GPT do? First token it will generate for. Then this for come to here. Just you see. Now it is come here as input. Then it generate every. Now after this prompt generate for, this for is appended here. Then again go every. Next every will come here and they will generate action. Then action is come here. So there. Then there is come here as an input. This is the next. Okay. Then is again come here and it's so on. So in this way that GPT is basically. Now you could say it is end by end of statement token. So this is where the GPT-2 or the GPT model is basically working. Okay. Now we have to understand what do we mean by masked self-attention. As you have seen, this is one of the major aspect in this is the masked self-attention. Encoder decoder self-attention we have seen before, but this is masked self-attention that we see. So here that one of the key difference in self-attention layer here, that is that it masks future tokens. Now it is a normal self-attention that all the words are going to take part to find out a particular word. But here you can see that if we have to go to this word, only the prior words are going to take part. So what it is saying, that not by changing the word to mask like part, but interfering the self-attention calculation, blocking information from tokens that are to right of the position being calculated. Let this position is being calculated. Okay, but these are the masked So self-attention is being calculated or being determined by the tokens prior to this, the particular tokens to be predicted. That is called the masked self-attention. This is very important to understand, one of the major concepts. Let's take an example to understand that in this masked self-attention layer, future tokens are masked. You see? So equal is the token we want to predict, and after that there is some tokens that is basically masked. So it is said that in the masked self-attention, future tokens are masked. The future tokens are not involved in the self-attention calculation. This block information from tokens that are to right of the position being calculated. So this is masked. This particular is being calculated, and this is the after tokens. After that, these tokens, they are all masked. That's the concept of the mask. Other things are very similar than the transformer decoder, what we have learned in very details. Now we are going to see how GPT-2 works. Technically, it doesn't use words as input, but byte pair encoding, the subword similar to words, is used. Okay, so this is the word embedding. After that, the positional embedding is incorporated and it is added to this, so that it understands the word position in a sentence, and then it is ready to go to this decoder part. It is easy to fine tune on your own data set. Okay. Now what is the advantage of GPT-2 over GPT-1, or what is the difference? It's almost identical, but as a layer normalization in between each subblock, as you have already seen, this vocabulary that the training extended to 50,000 to 7 tokens, and context has increased from 5 to 1 to 2. And this, the data size where on which it has been trained, is 8 million documents, but the common crawl, and but not Wikipedia. So these are the basic features. Now another important concept is GPT zero shot learning. Now what do we mean by zero shot learning? That it is a model's ability to perform tasks without any task specific training or finding. So sometimes if you imagine a situation that a model is not being trained on a particular images or text or something, but in test time this kind of data which has not been included in its training sequence being given. So just for example, to understand this hypothetical situation, a model is trained on the images of cows, images on horses, but no zebra images is given. But at the testing time, if the zebra images is given, can this model manage to predict that this is a zebra? This is the zero shot learning capability. Why zero shot? There is no prior knowledge or no prior training examples have been given to the model. Still it can manage. So this zero shot learning capability for GPT-2 refers to the model's ability to perform the task without any task specific training or finding, relying on that knowledge it learned during the pre-training. And GPT-2 has this capability. So GPT-2 can understand and respond to it just prompt without seeing labeled example before. So it is so powerful. So here it is, the translate English to French, good morning. This output is. So even though it was not explicitly trained on translation, it can still perform the task. And this is the. So GPT-2 is trained on massive text data containing many patterns. So that is why it able to do this. Since it is trained on a massive text data, it learns many patterns, question, translation, summaries. During inference, it recognizes the pattern in the prompt, and it generates a response based on the similar pattern data. Even if it is not present, by knowing the similarity of other patterns, it can predict it. So what is the advantage? It eliminates the need for task-specific dataset and makes GPT-2 flexible across many tasks and into the idea of prompt-based learning. But it has a weakness also. In general, the performance is weaker than finding models. Definitely, it is trained specifically for a particular task. They're highly dependent on the prompt. That means if we write a very efficient prompt, then it very useful. But if you prompt very weak, then it may not work as intended. And struggle with the complex or precise task. So these are the GPT with zero shot learning capability. Now, what is the application of GPT? Nowadays, lot of applications in conversational AI, in ChatGPT, everybody. Content generation, language translation, text summarization, answering, code generation, education tutoring, and many more. Why not that this application of GPT is everywhere? Since it's a generative model, it's a content generation. Translate one language to another. Given a text, it can summarize it. Given a question, it can answer. Some code it can generate. And some education and tutoring purpose also GPT is used. Okay. Now we are going to introduce another very interesting transformer based model, which is called vision transformer. As of now, whatever we have discussed, that's encoder only model, decoder only model, or encoder decoder model, all are transformer based model which are basically used on text data. Now, can it be possible that this transformer model can be used on the image data? A vision transformer is such kind of model where an image can be analyzed or a model can work on the image to infer something. So by definition, a vision transformer is a deep learning model that applies the transformer architecture, and what is introduced, this attention is all you need paper, to the image processing task. And that is one of the major importance of the vision transformer. Now, as we have seen that CNN is used, very frequently used on the image processing task. So in this VIT, instead of using convolution layers like traditional CNN, this splits an image into fixed size patches and treats each patches as a sequence of tokens and process them using self-attention to capture the global relationship across the image. Now consider a situation that you are given an image. You divide this image with several patches. Now you can scan these patches, row measure order, column measure order, or zigzag order, whatever order you want. Now what is it look like? It's a sequence of image patches. And this sequence has some sort of sequential context, or somewhat they are related in a sequential manner and sequential order. And that thing is being taken into consideration by V90. So this is important, that it treats each patch as a sequence token. So each patch is a token now, and a sequence of token is being prepared and process them using self-attention to capture the global relationship across the image. If we find out this, what is the relation between all the tokens, we can get a global relationship across the image. Because basically what is the patches is a part of the image only. So these capabilities allows this model to understand both local and long-range visual patterns effectively. When we see each patch, it's a local statistics. When we put the patches in a sequential and try to understand the relationship between this sequence or these patches in a sequence, it is global statistics. So this particular model not only understands the local, the patch based, and the long range visual patterns, that means the relationship interpatches in a particular sequence, effectively achieving a strong performance in tasks such as image classification, object detection, image recognition when trained on a large dataset. So vision transformer is one of the very good solution for the image processing from the transformer architecture point of view. Now you can see this is taken as the main paper. Here what we have seen, that these images are divided in patches and then it put in a, just you can say, row measure order. This is the sequence of patches. Then we can say linear projection of flattened patches. We can do it. And then we use some embeddings, patch embedding followed by a position embedding. And then it put it to the transformer encoder. So it is somewhat encoder based model. Then there is a encoder head, so it will get the analysis of some contextual information based on an create so different classes. So here you can say this is a transformer encoder, this embedded patches, then this kind of renormalization, after that the multi-transmission, then and there is a residual, then again the normalization and this MLP. And such encoder is a different level of encoder, whatever we have seen in the normal transformer encoder based model. So this is the vision transformer architecture in a very simplistic way to understand. Now an image is split into, what we have seen, that image is split into fixed size patches, linearly embed each of them, add position embeddings and feed the resulting sequence to vectors to a standard transformer encoder. So that we have just seen here, that it is first making the patches of images, then this we make a sequence of this, then linear projection of flattened patches, and then you put it in the transformer encoder and there is a head to classify. In order to perform the classification, the standard approach is to adding an extra learnable classification token to the sequence. Okay. The illustration of the transformer encoder was inspired by this Chwani paper. Okay, that is the main architecture of model architecture of the transformer. Now this model is almost identical to the BART, and instead of word as input, the inputs are P to B, P by P pixel image patches, and there is no overlap there. Each patch is embedded linearly into the vector size of 1, 2, 4 and 1D positional embedding speed. So these are the basic idea of Gaussian transform. So it is basically an encoder on level, very much like the BART. And word embedding is done, the inputs are P into P, and P by pixel, P pixel by P pixel images patches. And P may be 14, 16 or 32, and there is no overlap. And each patch is embedded linearly into the vector of size 1 and 1D positional embedding. Okay. Now how it is being trained? For pre-training, optimize the image classification of large supervised dataset. Imagine it 21 kg FT300, same set of CNN. Or fine tuning the smaller dataset, CIFAR 10, CIFAR 100 may be used. And there is a patch positional encoding. PIT learn 2D position information from 1D position. That's how the patches are positioned in this image. So this is the vision, very important image processing. So in this lecture, we mainly focused on generative pre-trained transform GPT, where we discussed different things of decoder only transform, GPT architecture, pre-trained and fine-tuning of the GPT, the concept of masked self-attention, and how the GPT with zero-shot learning and application of GPT. Then we introduce a vision transfer very briefly. In the next lecture, we start deep learning for vision application. Thank you very much.